the ME-189 engine testbed development project. And as you can see above, I'll just give a brief introduction of our team's composition. In the back row, there's our advisor, Professor Vince McDonald, and next to him is our head engineer, Richard Hack. They're both affiliated with the Advanced Power and Energy Program, which I'll introduce after. In the front row, there's me, Katie Leon. Next one over is Danny or Daniela Lopez. Following that is Ivan West, and then Christopher Farrell. This is the first introduction slide, just to give you a brief overview of the following slides. First, I'll talk about the Advanced Power and Energy Program. Moving on after will be Danny to talk about the engine generator testbed, and also to discuss a little bit about our desire to test this with alternative gaseous fuels and the resulting emissions data. So the Advanced Power and Energy Program is our sponsor and project oversight. They actually conducted a project a couple years ago that covered natural gas-fired microturbines. It was to discuss the emissions results, and what they found was actually very unexpected. The biggest component in the emissions that they found was PM2.5. As a quick context, that's particulate matter, which is 2.5 microns. To give a little bit of a scaling, it's approximately 50 times smaller than the width of a human hair. As you can imagine, it's extremely detrimental to heart and lung health, and will especially affect people with predispositions such as asthma. And the problem with this is that it can get deep into the lungs. Furthermore, this gives the basis for the project in which they wanted to have a test bed to measure the emissions criteria pollutants that result from a natural gas-fired reciprocating engine, which you see in many applications such as stationary power generation, gas and water pumping, as well as in vehicular applications. Moving forward is Danny for our generator.
Yes, that's me. Thank you, Katie. So the initial project plan was to buy a Volkswagen engine and connect it with the AC generator to make a system to be our test bed. Luckily, we instead were donated a 2002 50 kilowatt Generac generator from an outside source. The Generac engine in the system is like a Chevy V8 5.7 liter engine, and it runs on natural gas. And the fact that it runs on natural gas is actually very beneficial to us, so that way we can use other gases such as biogas or synthetic gas to compare data. This is our far quarter scheme, and since the donator mentioned that there was something wrong with the engine, we really wanted to make sure to start off the quarter by diagnosing the engine and finding out what was wrong with it, and by the end of the quarter we would have everything fixed and it running. And also, step one was to establish a setup for our workspace. Since this generator is very big, large, and heavy, we had to make sure we could find a place for it. And also, we then wanted to diagnose the engine and replace anything that was not functioning. A compression check and also an electrical installation check soon followed, so we could analyze the results and establish a component overload. Above, you can see our flowchart, and what is green was completed during fall quarter, and the gray at the end had to be pushed over to the next quarter, mostly due to waiting time with parts and ordering, and also we had to wait for a specialist to look at the installation check to make sure we can carry on forward with our future plans. I will pass it on to Chris, who will be more detailed about this.
Hello. So as Danny mentioned in the previous slide, the very first step we had to do upon receiving the generator was to run a diagnostic check on it. A diagnostic check basically consists of looking around the generator engine and seeing different parts, seeing maybe what parts need replacing, what parts were broken, different things along that aspect. One of the very first things we found was that the cracked fan belt sheath near the exhaust at the back of the engine was actually cracked. So we had to go ahead and remove that. And what we're doing is, at this point, we're going to be running the engine for not a long period of time due to perhaps maybe overheating. But we're hoping to replace that engine, or we're hoping to replace the fan at some point in the near future. Next, we noticed that one of the pressure regulators near the front of the engine test bed was missing a spring. As you can see, it's the bottom right-hand picture. The silver part's missing the spring, it's on the left. So what we did was we went ahead and replaced it so that we can now accurately measure we can now actually accurately change the pressure to reach the desired levels that we want. Another step we needed was the battery. We noticed the battery can no longer hold a charge, so we had to go ahead and replace that. As you can see, that's actually the old one. We replaced it with a nearly identical one, added a switch so that when it was running, we could just turn it on as running, turn it off so that it wouldn't discharge. And we also have a charging station as well, so that when we're not running, we can put it there. And lastly, we found that when we had the distributor cap in the engine, it didn't have a rotor in it, so we just went ahead and replaced the distributor cap since it was old anyway, and bought a new rotor replacement, so now we can actually go ahead and fire it. Next slide. The installation check we did was to measure the safety of the generator, whether or not it's safe to use in the practical sense. So what we did was we measured the resistance between the ground and 3 of these Y-shaped coil wires, which we found were in pretty good condition. And typically you want a resistance to be a very high value, something in the 500 to 1,000 mega ohms is what is typically found in industry. But our calculation gave us something around 0.2 mega ohms, which is on the low end. But we had a specialist come out, generator specialist, and they said that that's still a high enough value to be considered safe, so we didn't have to worry about that as much. And now I'm going to give it to Ivan, who will be talking about engine turnover and compression checks.
Yeah, thank you, Chris. So an important part of diagnosing an engine is to make a compression check. This will give you an idea of the condition of the engine valves and pistons in the cylinders. So what you do is you measure the pressure that builds up in the cylinders when the engine is turned over. So how you do this is you remove all the spark plugs from the engine, so there's no load or under pressure in the engine. Then you take one at a time, you plug in a pressure meter into the plug where you usually have the spark plugs, and you crank the engine over about 3 times, so the pressure builds up and stabilizes, so you get a correct read from it. During the first time we turned it over, there was oil spitting out of one of the cylinders, which could be a really bad sign. We could indicate an oil leak in the engine. But as we tried several times, it stopped, which we think is simply because there was oil sitting in the cylinder from the transportation. So we did the actual compression check and did that this year for every 8 of the cylinders. So the pressure was about 220 psi, which is a good amount. And besides cylinder 5 and 6, which was way lower, at least cylinder 5. So we poured automatic transmission fluid into them to make it more not leaking between the cylinder and the pistons. And the pressure went up, which is good, but it could also indicate bad O-rings. But as cylinder 5 was the worst one, but it's not that bad. It's still 170 psi, which is a good enough amount. So we went ahead and just thought it's okay for now. But we're gonna redo the compression checks at a later point, maybe next week. Yeah. So last quarter during the fall design review, we got a lot of feedback that people asking us why we didn't just buy a new engine, a new generator, instead of wasting our time trying to fix this and diagnosing and repairing. So there's 2 major reasons why we didn't do this. The first one is purely financial. To buy new systems would cost a lot of money. Obviously, we have estimated values here for either buying a new generator system that's comparable to the one we have, or buy a separate engine and a separate generator to hook up together. And these are produced engines and generators. So there could be other complications if you buy a used one. There could be some other problems showing up. And also, if you buy a separate engine and a generator, it's going to take time to hook it up in the right way. But the other big reason why we didn't buy a new engine is because of the experience we get from doing all these diagnostics and repairs. It's really invaluable when we're going to move on with our project and do the actual designing of the measurement equipment. So, yeah, and also as an engineer, it's very important to be able to work with what you get, instead of just as soon as something's not working exactly how you want it to, just buy new stuff. It's not a good way to solve problems. And for me personally, as an exchange student here, I think it's been a really good experience to have hands-on education, not just reading from a book. So I think we all feel very confident with all the parts of the engine, how it works, so we can move on with our next part of the project.
That's it. So after fall design review, we had to adjust our winter quarter goals. The main goal this quarter was to have the engine running on natural gas and start thinking of the parameters that we need to be taking down. So making instruments that would measure it. And we managed to correct the placement of the first piston, making sure that it was at top dead center, so that way all the others would follow. And we also, using the operating manual, we used the schematics to make sure all the connections were together in the generator portion. And the engine has now run successfully. And we are also, we have also identified the parameters that we need. So by the end of the quarter, we're hoping to have all instruments done and all parameters ready to be taken down on an Excel sheet. So that way we can have everything set, so the next quarter is just mostly analyzing it, taking down, collecting data. APEP has been a very great resource. Since they already have the fuel we need, all we needed to do is connect the engine to their resource. And we wanted to make sure we had valves on the hose. So we found a hose in APEP that we could use that was long enough to connect to the source of natural gas and to the inlet of our engine. We wanted valves to make sure we have better control, so we ended up cutting some valves off of some pipes and making sure they fit well. And we also needed to make sure that the pressure was correct. So in the manual it said it needed about 11 to 14 inches of water for its pressure, and this is very low compared to the pressure gauges that APEP has, which has like 300 psi, and we were just making sure it was like maybe less than 1 psi, so we ended up using a manometer. And in the upper right-hand corner is a video of our engine running, but due to time constraint, maybe if we have time at the end, we would show that. On to Chris for parameter definition.
Okay, so this is a preliminary list of the parameter definitions we've come up with that we want to test for, either coming up very soon or maybe potentially at the beginning of next quarter. Some of them include pressure, temperature, and volumetric flow rate. Some of the instruments we would use include thermocouples, pressure gauge sensors, or a roots meter. For the airflow rate, we're actually going to design a Venturi meter ourselves. One of the things that we'll be making using SolidWorks and coming up with ourselves. So that will be a very interesting experience for us designing something as an engineer for the first time. Next slide. Future tasks for the quarter include assessing the engine complications while it's running. So we did diagnostics check while it's standalone, while it's not running. So now, what if it's running? What if we encounter more problems that we might have to fix? So we're going to have to deal with that. Next, we're going to design and manufacture measurement equipment, which I talked about last slide, namely Venturi meters to measure flow rates. After that, we will implement these measurement equipment to the engine and start taking data, probably early next quarter. And some of the measurement equipment we don't have to design that APEP is already willing to supply us with, including manometers, pressure sensors, and emissions tests as well. Next, I'm going to hand it off to Katie.
Okay, so for the spring quarter goals, we will be ensuring that the engine is running reliably with the tools implemented. We will further conduct performance and efficiency tests in comparison to the calculations that we would expect to see from our engine, as well as taking emission samples. After this, we'll analyze these results and then present them in conclusions. And we also plan to create a document for future researchers after us that will be utilizing this test bed. And also for future implications, as we discussed recently with our advisor, we may not be able to conduct the PM 2.5 testing ourselves because it is really intensive. It takes a lot of time. And the main goal of this was to have a completed test bed, which, based on where we're at currently in the project scope, it looks as if we will be able to reach those goals. We also hope that any of our just standard emissions results, we may be able to extrapolate to other applications such as vehicular applications, also learn some of the trends on how emissions are created and mediated as well. And with that, it wraps up our presentation. Thank you very much.